In this PowerPoint, we're going to continue our exploration of thermodynamics by introducing the concept of Gibbs free energy. Gibbs free energy is a measure of chemical potential energy, and it gives us another method for determining whether or not a chemical process will occur spontaneously. In a previous PowerPoint, we said that processes that are spontaneous, meaning they occur on their own, increase the dispersal of the matter and energy in the universe. We then defined entropy as a measure of this dispersal. There is a second way of determining spontaneity of a chemical process that does not involve trying to assess the entropy changes of the entire universe. Changes are also spontaneous when the potential energy of the system involved decreases. Here's a simple example. You know that a brick being held at a height above the ground has potential energy because of the force of gravity acting upon it. If you stop holding the brick up, it will spontaneously fall. And while falling, its gravitational potential energy is converted into kinetic energy. So the spontaneous process of falling decreases the potential energy of the brick. The same concept applies to chemical systems. The potential energy of the substances involved in these systems is known as the chemical potential energy, or Gibbs free energy. Gibbs free energy is defined as the chemical potential of the system. It represents the enthalpy of the system, H, minus the temperature of the system in units of Kelvin, times the entropy of the system, S. Now, measurements of energy, like enthalpy or Gibbs free energy, can only be measured during a change, as energy is released or absorbed. As a result, a more useful definition of Gibbs energy is the change, delta G, of the system is equal to the enthalpy change, delta H, of the system minus the temperature times the entropy change, delta S, of the system. You might notice that this is similar to our definition of the change in entropy of the universe that we used in previous PowerPoints. But there's one important difference. It turns out that the change in Gibbs free energy is proportional to the negative of the entropy change of the universe. In other words, when the entropy change of the universe is positive, when it increases, the change in Gibbs free energy for a chemical system will be negative. It will decrease. Let's look at this relationship again. We know that when the entropy of the universe increases, or delta S universe is positive or greater than 0, for any particular process, that process is considered spontaneous in the forward direction. In other words, reactants are transformed into products spontaneously. Since the change in Gibbs free energy for the system is proportional to the negative of the entropy change of the universe, this also means that a reaction is spontaneous in the forward direction when we have a negative value of delta G for the system. In the opposite direction, when the entropy change of the universe is negative or less than 0, then the delta G of the system will be positive or greater than 0, and the process will be considered non-spontaneous in the forward direction. In other words, this reaction would have to have a continual input of energy to make it go forward. But what happens when the entropy change of the universe and the Gibbs free energy change of the system are both equal to 0? When this happens, it's a special situation associated with reversible processes. At this point, the system is considered at equilibrium. In other words, the process is reversible with neither the forward or the reverse reaction favored. As a result, the system's reached a steady state in terms of the concentrations of the reactants and the products. There are two major methods for calculating the Gibbs free energy change for any process. The first is to use measured or calculated values of the enthalpy change of the system, delta H, the entropy change of the system, delta S, and temperature, along with the Gibbs free energy formula of delta H system minus the temperature times the delta S of the system. The second method involves using standard thermodynamic reference values for the free energy of formation of the reactants and the products. We'll review both methods in this PowerPoint, but we'll start with the first one. Let's calculate the standard Gibbs free energy change at 298 Kelvin for the phase change of water from liquid to gas. To do this, we're going to use the standard enthalpy of formation and absolute entropy values that are found in the appendix at the back of your textbook. Now we know that the change in Gibbs free energy, delta G, is going to be equal to the change in the enthalpy of our system minus the temperature times the change in entropy. None of our given reference values stands for the enthalpy change of the system or the entropy change on their own, but we can use them to calculate these changes. For enthalpy change of the system, which is the same as the enthalpy change of our reaction, it's equal to the sum of the enthalpy of formations of our products times their molar coefficients minus the enthalpy of formation of our reactants, their sum, times their molar coefficients. So we actually have only one product, gaseous water, and one reactant, and both of those have molar coefficients of 1. So we can simply take the difference between our product and our reactant in terms of their enthalpy of formations. So delta H of our reaction is equal to the negative 241.82 kilojoules per mole for the enthalpy of formation of gaseous water minus the negative 286.83 kilojoules per mole for the enthalpy of formation of our liquid water. We plug this into our calculator and we get a positive value, 44.01 kilojoules per mole. So this process is endothermic. We can do a similar calculation for the entropy change, delta S, of the reaction. Here, instead of using enthalpies of formation, we substitute in our absolute entropy values for gaseous and liquid water. 188.8 joules per mole Kelvin minus 70 joules per mole Kelvin gives us a positive value for our entropy change, 118.8 joules per mole Kelvin. We can now use these calculated enthalpy and entropy changes to calculate the change in Gibbs free energy, or chemical potential, of our system. We do need to make sure that the energy units are the same before plugging them into our formula. So I'm going to convert the entropy from joules to kilojoules by dividing by 1,000. So the value for the entropy change of the reaction that I'm going to plug in is actually 0.1188 kilojoules per mole Kelvin. I take this value and multiply it by 298 Kelvin. My kelvins will cancel out. It'll give me kilojoules per mole, and I subtract the product from 44.01 kilojoules per mole to give me the Gibbs free energy change, positive 8.59 kilojoules per mole. So this indicates that the chemical potential energy of the system actually increases for this process at 298 Kelvin. In other words, this process is considered non-spontaneous at 298 Kelvin. So liquid water does not boil spontaneously at standard room temperature. While water does not boil spontaneously at 25 degrees Celsius, it does boil spontaneously at 100 degrees. This is a common scenario. For many processes, the spontaneity is temperature dependent. get the temp into the right range, and the reaction will move forward. The equation used for calculating delta G in method 1 helps us pinpoint this temperature dependence. In order for delta G to be negative, which is what we need for a spontaneous process, our second term in the equation, the temperature times the entropy of the system, has to be larger than the first term, the enthalpy of the system. This balance, it turns out, is going to depend upon the sign of delta H, the sign of delta S, as well as the magnitude of the temperature. Let's look at a few scenarios. For our first scenario, we're going to look at an endothermic reaction that increases the entropy of the system. So endothermic reactions have a positive value for delta H. An increase in entropy of the system indicates a positive value for delta S. A classic example of this is going to be the process of boiling. To go from the liquid to the gas phase, it does require heat energy, but the gas phase is considered more disordered or dispersed than the liquid. So our products have a higher entropy than our reactants. Now, in terms of the equation, we have a positive value minus another positive value. The only way that we're going to get a negative value for our delta G is going to be if that second term is larger than the first. And this will happen when the temperature value is higher. So this process is considered spontaneous at higher temperature values. If that temperature is too low, then the second term, temperature times delta S, will actually become smaller than our delta H term, and our balance will be positive or non-spontaneous. So at lower temperatures, this type of process is non-spontaneous. And we see this for the process of boiling. Boiling occurs at higher temperatures, but not at lower temperatures, not below the boiling point of that particular substance. So to put this into other terms, the increase in entropy from reactants to products favors a spontaneous process. However, the requirement of heat for an endothermic reaction favors a non-spontaneous process. If the ambient temperature is high enough to provide that heat, the increase in entropy overall makes the reaction spontaneous. For our second scenario, we're going to look at an exothermic process that decreases in entropy from reactants to products. So exothermic means a negative value for delta H, and a decrease in entropy from reactants to products is a negative value for delta S. Another classic example is freezing. Going from the liquid to the solid phase does require a release in heat energy, but the liquid phase is considered the more disordered or dispersed of the phases. So our reactants are actually have a higher entropy value than our products. In terms of the equation, we have a negative value for delta H minus another negative value for delta S. So minus a negative makes a positive. In order to keep the balance negative overall, this time our second term must be a smaller negative value than our first term. So that means when T, our temperature value, is smaller, it's going to keep this second term ultimately less than the first term, so that we end up with a spontaneous process overall at lower temperatures. If the temperature term increases, though, it will make this second one larger, a more negative value, which ends up overbalancing the negative of the enthalpy, our first term, and we end up with a positive delta G. And so it becomes non-spontaneous at higher temperatures. So exothermic processes favor spontaneity, but a decrease in entropy does not. At lower temperatures, we actually minimize the change in entropy term over the enthalpy term. For our third scenario, we're going to look at an exothermic reaction that also increases in entropy for the system. So a negative value for delta H and a positive value for delta S. So this time in terms of our equation, we're looking at a negative minus a positive value. So a negative minus a positive will actually always give us a negative value overall. It doesn't matter what the temperature is on that second term, it's always going to essentially make the first term even more negative. So we end up with a spontaneous process at any temperature. Both of these terms, an exothermic process, a release in heat energy, and an increase in entropy for our system, tend to favor spontaneity. So they reinforce each other and we end up with a spontaneous process overall. It's the opposite for our last scenario. Here we have an endothermic reaction with a positive delta H and a decrease in entropy from reactants to products with a negative delta S. So in this case, we have a positive value minus a negative value. Minus a negative makes a positive again. So it ends up being two positives together, which are always going to give us a positive for delta G. So this type of process, endothermic reactions that also decrease in entropy, both of these tend to favor non-spontaneous processes, go against spontaneity, and we end up with a non-spontaneous process at whatever temperature that we're looking at. While method 1 of calculating Gibbs free energy change illustrates more clearly the balance between enthalpy and entropy changes, as well as the effect of temperature and spontaneity, method 2 can usually be done more quickly if you have a table of standard thermodynamic reference values. This is because most of these tables provide a third column of reference values. So in addition to the standard enthalpy of formation, delta H, and the absolute entropy, S, the third column is usually the standard Gibbs free energy of formation, or delta G with a subscript F. So this third column on your standard thermodynamic reference table represents the Gibbs free energy change for the formation of the substance listed from its constituent elements. The F subscript indicates the formation reaction, and the general form for that reaction is listed here. It's always the individual elements that are found in the substance listed on the table as the reactants on the left-hand side, and the substance listed, its formula, as the final product on the right. You'll never see this reaction written out on the table. You'll only see the formula and state of the final product listed, and really that's all you need. The degree sign, as a reminder, indicates standard thermodynamic conditions. So this means it's the Gibbs free energy of formation for that process at 25 degrees Celsius or 298 Kelvin. All gases that are present are assumed to have a partial pressure of 1 atmosphere. Liquids and solids are in their most stable form, and any solutions have a concentration of 1 mole per liter. We can use these standard reference values for delta GF to calculate the Gibbs free energy change for any process the same way we use the other thermodynamic values. So the standard Gibbs free energy change for any reaction is simply equal to the sum of the Gibbs free energy of formations, delta G sub F, for the products in that reaction, times their coefficients from the balanced chemical equation, minus the sum of the Gibbs free energy of formation for the reactants in that process, times their coefficients from the balanced chemical equation. Let's calculate the standard Gibbs free energy change at 298 Kelvin for the oxidation of methane gas to carbon in its graphite form and gaseous water. So to do this, we need to look up our standard reference values. When we look at the appendix in the back of the book, For these particular substances, we find the full set of data. So we see here our enthalpy, our absolute entropy, and our Gibbs free energy of formation values. Now we could certainly use the first two columns, calculate the change in enthalpy for our reaction and the change in entropy for our reaction, and then use the formula that we did in method 1. But since we have the Gibbs free energy of formation data, it becomes much simpler to just substitute this into our formula for the Gibbs free energy change for the reaction. So we add together the Gibbs free energy of formation of our products and subtract from it the sum of the Gibbs free energy of formation of our reactants. Now you'll notice that both carbon and oxygen have Gibbs free energy of formation of 0. This is because they are their elements in their most stable form, and like enthalpy of formations, the Gibbs free energy of formation of elements in their most stable form, it's always 0. So we substitute these into our equation, and we have 0 for the Gibbs free energy of carbon as graphite, our first product, plus 2 times the Gibbs free energy of formation of our water, gaseous water, as our second product. And we subtract from this the sum of our reactants. So we have 1 methane at negative 50.5 kilojoules per mole for its Gibbs free energy of formation, and 0 for the oxygen Gibbs free energy of formation. We plug this into our calculator and we get a value of negative 406.68 kilojoules per mole for this process. A negative value indicates that it is spontaneous under standard conditions, 298 Kelvin and 1 atmosphere pressure for all of the gases. What we also see is that this process, this calculation for Gibbs free energy, is much simpler when we have these standard reference values for Gibbs free energy of formation. So in summary, spontaneous processes result in a reduction in the chemical potential energy of the system. The chemical potential energy of the system is defined as the Gibbs free energy, G, and negative values of delta G indicate spontaneous processes. The change in Gibbs free energy, delta G, is a balance between the enthalpy change for the system, delta H, and the temperature times the entropy change, delta S. Delta G values can be calculated as well from standard thermodynamic reference values.